Good morning, everyone. My name is Sungbin Lee from KAIST, Korea. And today I'm going to talk about this exerting magnetism in quasicrystals. And I'm always good to be back to Santa Barbara and meet former advisors and many friends. And thanks for organizers for inviting me to this nice workshop. So all of this work in terms of quasicrystals has been done with my student, Junmo Jeon, who started from the scratch. So sometimes he teaches me how to think about quasicrystals. And I also would like to special thanks to one of my sons who traveled with me. So who's walking around the KITP, sitting all day in the KITP library. So he's enjoying anyway. So here's the outline of my talk. So first of all, I'm the only one who are discussing these quasicrystals. So I will give you an introduction how we can think about the quasicrystals. And then one of the important features in the quasicrystal, we call it as a critical state. I will introduce what that is and how we can control this. And then I will introduce some of the interesting previous works in quasicrystals. And then related to the magnetic properties, I will discuss two aspects, the multipolar physics and also anomalous RKKY interactions. And finally, I will summarize. So quasicrystals has been long-standing. So first discovered by Dan Sheltman for these forbidden electron diffraction patterns in the conventional crystals. And then you may have seen this magic eye like pretty Penrose tilings, which has bifold symmetries. And also there are also three-dimensional version of these. So there are many, many interesting quasicrystals present in nature. But how one can think about these quasicrystals? So the simplest example is 1D. So you may have heard about this Fibonacci quasicrystal. So this is the sequence. You have two tilings, short and long. So whenever you see this, following this substitution rule, whenever you meet long, then you substitute as long, short. And then whenever you meet short, then you substitute as long. So following the generations, then following these substitution rules, then you will find the exactly ordered but never periodic structure, which we call it as Fibonacci quasicrystals. And the interesting thing, another way to think about this Fibonacci quasicrystal is the projection from the high dimension. So if we think about this two-dimensional square lattice, and then you can divide into with some irrational angle, in this case, Gordon ratio. And we have this physical space, one-dimensional space, and then you have some kind of perpendicular space with finite window. So whenever you have the sites within this finite window, then you project into this physical space. So then you have recover this Fibonacci quasicrystals. So this method, we call it as cut and paste method. So there are many interesting quasicrystal structures, even in 2D. As I mentioned, what's interesting? So it allows some general n-fold rotational symmetries. So we know if we have periodicity conventional crystals, then we only have this restricted n-fold rotational symmetries. But as I mentioned, for Penrose tiling, we allow this bifold symmetry. And if we think about from high-dimensional hypercubic lattice structure, then it's coming from the projection of 5-dimensional hypercubic structure to 2-dimensional. And also we can think about this Binker tiling, which we have 8-fold, which coming from 4-dimensional simple cubic lattice projection to 2-dimensional physical space. So we can think about there are many, many different materials, and most of them are kind of alloys with these transition metals. So this is, you see these diffraction patterns, indeed, we have some kind of bifold symmetry. And the most well-known example for this quasicrystal is this chi-type icosahedra. So it's probably complicated, but it's three-dimensional bulk, and if you think about two-dimensional surface, then it's nothing but the Penrose tiling. And this chi-type icosahedra that I will discuss later in more detail, it's coming from the 6-dimensional hypercubic lattice structure projecting to the 3-dimensional physical space. So there are many, many candidate materials and existing present in nature with these aluminum copper irons or these catechite minerals. So there are nice papers which list all the present materials for quasicrystals. And very recently, I think Paul Steinhardt found this fossilized lightning, which is formed by a strong electrical discharge through a sand dune. They claim that they discovered new quasicrystal, which has 12-fold symmetries with these complicated combinations. And also, in terms of magnetic quasicrystal, there exist some of them. So if you look at this gold, aluminum, and rare earth, ytterbium, there are many different kinds. So then you can think about all these cages, concentrosymmetric. So it's kind of concentric shell structure you see, starting from this smaller shell, and then you have larger and larger shells. So this is nothing but chi-type clusters. And if we include all of them, it's horribly complicated. But if we just consider these ytterbium sites, then we have this kind of already complicated, these chi-type quasicrystals. And the interesting aspect in terms of this magnetic quasicrystal is known that we have some kind of diverging magnetic susceptibilities and also some kind of non-Fermi liquid physics, which are not well understood. And also there are some magnetic quasicrystals recently known, where most of the quasicrystals, they see some kind of spin glass behavior. So if we have most of the cases, very low temperature, then we have some kind of freezing behavior. But these quasicrystals, which is combination of this gadolinium or terbium, we have this long range ordering with some intensities, black pink. So that has been highlighted a couple of years ago. Not only the present in nature, but also there are some attempts to discuss these artificial quasicrystals. This is like polymer dispersed liquid crystal material using multi-beam hololithography. I don't know all the details, but there are some attempts to trying to realize these quasicrystals. And also we have using nanomagnets, interacting nanomagnets, they realize these different types of Penrose tilings. And also I think it's from this UCSD, David Well group. So they looked around these kicked Andre Harper quasicrystals, which is nothing but, if we look at the Hamiltonian, then you have this kind of with incommensurate, this alpha, you have this non-incommensurate potentials, and you have some kind of time periodic. So you have Floquet type, Floquet version of this kicked, the Aubrey and Andre Harper quasicrystals using this cold atom, strontium atom. And they found that interesting Floquet engineering and results this kind of critical states. So I will talk about critical states later in more details, but this is the last slide where very recently, from mathematicians' point of view, it was long-standing question. Can we make any single monotile quasicrystals? And it's recently discovered that it's possible. And this whole complicated shape, these T-shirts kind of, or hats from single tiling with 13-sided shape, they can make these quasi-periodic structures fully cover this two-dimensional space. And this they call also as an Einstein tiling, which is nothing to do with Albert Einstein, but in German it's called one-stone. So it's kind of a single tile realized quasicrystal. So what's interesting in these quasicrystals, of course, we don't have any periodic length scales, okay? But we have some kind of self-similarity, which I will discuss. And as I mentioned, we allow some n-fold symmetries. So because we don't have any periodic length scales, we cannot use Bloch theorem. We don't have any good momentum space. So it can be blessing or curse. So, but interesting thing for this quasicrystal is we can have the electronic states which neither localized nor extended. So how can we understand this, the critical states? So this is the Fibonacci tiling, wave function spectrum at zero energy. So you can just simply put with Fibonacci sequence, you make long or short hopping as different numbers. So then this is the wave function magnitude, and these different plots is nothing but you zooming in or zooming out. So this is the plot within 2,000 sites, and then you zoom in to 300 sites, and then you further zoom in to 50 sites. The structure looks the same. So it's kind of self-similar. And also, we have seen this power law decaying of the wave function. Okay, that's something interesting. So how one can understand this power law decaying of wave function, and the exact analytic approach has been quite recently known. So it's these critical states, if we starting from this simple hopping model, and then for depending on odd or even side, at zero energy, we can just exactly writing down the Schrödinger equation. And then by defining their ratio between the long and short hopping, then we can find this rho with this function, which is this A function is nothing but the hopping constant arrangement between 2n sides to 2n plus 2 sides. So for instance, if we have 3 sides with 2 hoppings, it's long, long, we put A as number 0. If it's long, short, it's 1, and short, long, we put -1. But in this tiling, we can never find short, short. So we don't have such kind of short, short sequence. But with this, we can make the height field or the summation of this field. And then we can writing down our wave function with this height field in terms of this ratio. So then this height field is logarithmically increasing, as this is logarithmic scale. And we can find that our this height function is some kind of root square of log L scale. So that automatically guarantees that we have some kind of power law decay. So beyond these critical states, what's interesting? So as I mentioned, there's no periodic length scales, but what if we apply the magnetic field? So by applying the magnetic field, because of this unique structure, this is the example of Penrose tiling, but it can be applicable for any of the two-dimensional tiling. So at particular flux by 2, then we can make exact Aharonov-Bohm type destructive interference. So in other words, we can make the electrons are totally just localized within certain this length scales. So then in terms of cartoon, we can think about some given localization length scale, they form this kind of islands. And their islands is just, just everywhere. But if we change flux from this particular flux a little bit, then these islands interfere with each other. So starting from these localized islands, if we tuning the flux, then we can have this kind of interference between the islands, and it changed the localization behavior. And another thing that we found is interesting is whenever we do the cut and paste scheme, then this is the example for the Amand-Winkel tiling, which we have 8-fold symmetry. It's coming from the 4-dimensional hypercubic lattice projecting onto the 2-dimensional physical space with 2-dimensional perpendicular certain windows. But if we slightly change, not slightly, with some certain translation vector gamma, then we found that once it projecting, then we found that we have some new type of, but self-dimensional, this quasi-periodic pattern appears. And it also changes from 8-fold to 2-fold or 4-fold, depending on this gamma. So that's kind of interesting aspects in the quasicrystals, and not only for these Hermitian systems, but also we can think about non-Hermiticity if we can able to control this localization-delocalizations. So this is the Hamiltonian. You can think about just simple tight binding and also this the potential, but quasi-periodic potentials. And on top of that, you think about this non-reciprocal hopping phase. So in this case, what we found is starting from the localized state, if we tune this theta all the way to by controlling this theta, then we can tune our wave function to be localized to critical to delocalized state. So that kind of things are pretty interesting aspects. But in terms of magnetic properties, what can we say something new? So I first focused on this multipolar physics that you may all aware of. So in heavy fermion system, this hidden order is in heavy fermions are very famous, and you know that this hidden order, how one can tune with pressure or temperature or magnetic fields. And also from the Doniak phase diagram, if we have this competing RKKY and Kondo interactions, then how we can make the new phase diagram with some kind of multipolar degrees of freedom if they ordered. So most of these multipolar degrees of freedom, unfortunately, coexist with magnetic dipoles. So for instance, this spin-ice compound, famous cerium compounds. So then we have dipole-octopole frustrated spin-ice. But there are very few examples having pure multipoles in the conventional crystals. So one of them is by Professor Nakatsuji. So this praseodymium and this cage compound has exact gamma-3 doublets, where their pseudo-spins are described by this quadrupole and octupole degrees of freedom. On the other hand, this octopolar order also exists in these materials, where we have multiple cube octopolar order. So what are the ingredients everyone knows? So we have some delicate combination of crystalline electric field and spin-orbit couplings. So the question that I asked is, because in the conventional periodic crystals, we have very limited, of course, we have limited point group symmetries, but what about if we go to the quasicrystals? So we focused on this crystal field splitting, which if we have perfect icosahedral point group symmetries. So then these icosahedral point group symmetries under this, if we have strong spin-orbit coupling, we have to have these rare earth ions. So the question is, with icosahedral quasicrystals, can we have some kind of multiple degrees of freedom? Before we go to that, how one can make this icosahedral quasicrystal? It's pretty complicated. So you have this 6-dimensional hypercubic lattice, 2 3-dimensional physical space. So this is the projection map to the physical space. So whenever you have lattice sites, which in these polygons, then we project that site into the physical space. That's how we make these icosahedral quasicrystals. So with these crystal field splittings, we looked at ytterbium 3+, for instance. So then we have one hole for single hole ytterbium 3+, and with strong spin-orbit coupling and crystal electric field splitting, we found that in the environment of this gold or aluminum, which is present in nature, so then we found that these doublets were separated by other sextets. So this is written in terms of combination of different JZ elements. But interestingly, we found that if we have this kind of doublets, then we don't have any dipoles or quadrupoles. But these pseudo-spin half, plus, minus, or Z components are all described by these rank 3 spherical tensor operators. So if we're writing down these spherical 3 rank tensor operators, then we have this sigma Z is nothing but like JZ cube minus JZ square. So it looks like this. So this is always towards the center of the local Z axis is always towards the center of this icosahedral. And then we have this kind of octopoles. So with these octopoles, one can writing down what's the symmetry allowed spin Hamiltonian. So it's very similar to what people discuss. We allow many, many different terms, which is Ising term, plus minus term, and isotropic term, and etc. And if we allow some kind of anti-ferromagnetic interaction, Ising term, let's just focus on the Ising case. So then it's natural to think about, because of this triangular geometry, then we generally allow the frustrations. So with this frustration, we figured it out. We have 72 degenerate states even in a single icosahedron. And in more details, we have 60 with 5-fold and 12 with and without 5-fold symmetries. So what if the quantum fluctuation is present, starting from this number of degenerate states? If we add these spin flipping terms, then we found that particular superposition of these degenerate states are just forming the entire ground state. So indeed, if we turn on this J plus minus, then it's trivial that we will induce some entangled state with this superposition of particular 72. Yes? Yeah, these are lattice sites. Yeah, so we are just solving it in the single icosahedra. Yes. Of course, if we include further intershell coupling, that is more complicated. But let's just focus on a single icosahedra. So then, starting from this, we have as Chenka already asked, if we add this ferro or anti-ferro intershell, then it's pretty complicated. And we can think about that they have some kind of different types of ordering. But it's interesting to note that if we zoom out, then each of these shells, again, they form this kind of icosahedral. So we have this kind of 3 icosahedral shell interact geometrically frustrated case. It's self-similar. So then, in real material, we don't have this perfect icosahedral crystal field splitting point group, but we generally have just C5 in the absence of mirror reflections. So then we can just make the symmetry down to C5, and then we found that starting from these pure octopoles, most of all this Ising component spin just go to the dipole, has dipole, unfortunately. But most of these XY components, they still are described by like octopoles or dotary quintupoles, etc. So this is the different configuration for different J, half integer J. For integer J, where you have this quadrupole or hexadecapoles, which is multiple degrees of freedom. So it's very generic multipolar degrees of freedom can be present in the magnetic quasicrystals. So that's one lesson we earned. And the second topic is why we were studying this. Most of the magnetic quasicrystals are alloys, so it's conducting. So then we were asked, what if we have this critical state, and on top of that, if we have some magnetic impurities? As I mentioned, we have this power law decay, these critical states, and then can we expect some kind of anomalous magnetic properties because of the existence of critical states, which we never expected in the conventional crystals. So then we go back to this Fibonacci, the simplest case. And then this is a Fibonacci, this starting from LS, LL, or something like this. And then we know that we have this kind of critical states, and let's put some kind of spin on top of that and make them as condo-coupled. So what happens is conventional RKKY. This is the exact energy spectrum for the Fibonacci quasicrystals energy spectrums. And then usual case, the electron states near the Fermi level is dominantly contribute to the RKKY interaction. So if near the Fermi level state is extended, then we already know that our RKKY will be 1 over RDK, depending on the dimension. If it's not localized, it's negligible. So what if we have the critical states? So we found that if we changing the ratio of this long hopping and short hopping, if it's 1, then it's nothing but we perfectly recover the periodic chains. So we have 1 over RDK. This is the site index, and this is RKKY magnitude. However, what we found is if we deviate from this row to exactly 1, so we have some decoration with Fibonacci sequence, then we found that it's very non-monotonic, but we have very particular sites are very sharply picked with much, much stronger RKKY. So we found that long distance RKKY, like 1,000 sites far apart, are very, very strongly, 1,000 times stronger RKKY is being induced. So why that's the case? So it's actually coming from the critical states. So if we look at these eigenstates of energy 0 or near 0, then we found that there are some particular sites where it's highly picked. So when we calculate this RKKY, then these highly picked sites with large intensity in terms of wave function will strongly contribute. So at the end of the day, we have very non-monotonic, but at very particular sites, we have very strong RKKY interactions. So this is some kind of picture that not all the sites, but there are some particular sites where they have very, very strong RKKY interactions, not nearby. So we have this strong RKKY interaction because of this existence of the critical states. So it's important to note that depending on the tiling patterns, So far we've just discussed the Fibonacci sequence, but if we have different tilings, then we can control those kind of how strong the RKKY is and also how they are far apart. So this is when we have this substitution rule within the silver mean. And then we found that if this is RKKY, so then we found that there are particular sites which far apart, 10,000 sites far apart. They are 10,000 times strongly interacting, most strongly interacting. So we can have this, depending on the tiling, we can even induce some longer distance RKKY and stronger RKKY interactions. So this is the animation that I made, that my student made. It's not very good, but so what's doing here? So we first all polarize the spin along the z direction. And then now we locally flip one of the spin along x direction. And then most of the other spins, they don't interact, so they just stays there. But whenever there are some particular sites which are strongly connected by these RKKY interactions, they have this kind of same polarization along the x direction. Or depending on its antiferromagnetism minus x direction, something like that. So this is nothing but as a function of time, how this x changes, evolution. So here's the summary. So I'm kind of advertising the Quasicrystal is an interesting platform searching for interesting phenomena. And there, in terms of magnetic properties, there are, from my understanding, not many things are not known. And also interesting magnetic behavior, as I discussed, long range, long distance, RKKY, strong RKKY, also multipolar. Degrees of freedom are present. So I think the quasicrystal is an interesting materials. So I think with this, I will just thank you for your attention. Yes.
Thank you very much for a very interesting and beautiful talk. So can I ask a quick question about the end of your talk? So
yes.
When you have this very strong antiferromagnetic interaction, are you going to form some effective singlets?
Yeah, that's in principle possible. So if we consider this long range singlets, and then there are some other sites which far apart, and they can also form some kind of
some sort of random singlet phase, but
yeah, it's not exactly random.
It's not exactly random,
it's coming from the
but effectively,
right. So it's interesting to study, how this low energy, the spin. Once we integrating out all these singlets, it's embedded from the critical state.
And what if you switch magnetic fields on top of that? So you have this kind of rarely interacting spins, and then you have magnetic field. We would just some collective states for the whole system?
That I have to think about. Yes, that's a good question.
Thank you. Even before coupling different impurities, I have a simpler question. What is known if you start to disorder the critical? So if you take your Fibonacci chain and you break bonds or put impurities,
right.
What is known if you calculate IPRs or so?
So if we have certain amount of, very small amount of vacancies or some kind of disorder, then still, as long as we have very large Fibonacci sequence, then the critical state is still preserved. Okay. But I cannot tell you which percentage of these vacancies or disorder will break it.
Okay, thank you.
Thank you very much. So I have a question on experimental signatures. So of these reinforced RKKY, so what do you expect in experiments, or let's say, for instance, susceptibility experiments, that one could see this type of effect?
Yeah,
there are many experiments on this quasicrystals, but
so that's a very good question that we are pursuing. But unfortunately, most of the magnetic quasicrystals, they have no ordering, first of all, and most of them are freezing. So that's why I think the Takusato group has highlighted this long range magnetic ordering is present, very rare case. But in terms of, it's interesting question in if we consider this kind of existence of critical states to higher like 2D or 3D icosahedral type of quasicrystals, then can we think about some kind of general like spin glass because they are long range interaction, and that's open question. Yeah.
So I was curious how you get this 5-fold symmetry.
Yes.
Is this from this whatever cut and paste, or I forget, projecting cut and project procedure? That
yes. In terms of figure, I cannot I cannot give you, but as I told you, if we go to this the projection map. So if we look at let me just so we basically work on, because we don't have any good intuition for a higher dimension. So we have this 6-dimensional hypercubic lattice. And then whenever we have within this finite window, then we project into this physical space. And it turned out that we have this 5-fold rotation symmetry. So in order to do that, we have to select certain axes, which in the higher dimension, we have 5-fold rotation symmetry and projecting them out. But I don't have good picture of it.
Yeah, thanks for a very interesting talk. So you discussed the effect of magnetic field at certain strength of magnetic field. You have localized states, some array of localized states. So these localized states, maybe I missed, but these localized states also form a quasicrystal.
In which case,
you apply the magnetic field, and then
I see.
at certain magnetic
not
field.
For the magnetic properties.
You had the
This one.
Yeah.
Yes.
So these localized islands form.
Yes, they also form some kind of quasi-periodic structure because this cage has to follow this exact quasi-periodic patterns.
Then if you change the flux a little bit, then you have hopping between islands. So
yes,
effective Hamiltonian is like another tight binding type model on.
Yeah, we basically add this magnetic flux correction, and then we see this interference effect between the islands.
Then my question is that so I don't know what is the energy spectrum look like at this phi equals to exactly this number, but you know, does the energy spectrum of this effective tight binding model overlap with some other states, or these states are isolated in energy? So this is a really
so this
effective.
exact flux where they have this perfect localized island. It happens at zero energy, exactly at zero energy, which is not connected to others.
I see. So there's a gap to other states. Okay. I see. Good. Thank you.
Yes.
So my question is, you briefly alluded to the non-Hermitian Fibonacci chain, right?
Yes.
So I was wondering what's the fate of the skin effect there? Because for the Hatano-Nelson, we know that periodic and open boundary conditions gives the skin effect. And
so here, the thing is, we have considered as non-Hermitian is not the asymmetric T left and T right, the imbalance, but we consider this non-reciprocal hopping phase. So if we consider just usual T left and T right, the hopping to left and right is imbalanced, then we generally allow this skin effect, non-Hermitian skin effect. But in this case, because we allow different types of non-Hermiticity by this non-reciprocal hopping phase, we don't have such kind of skin effect.
You just too quick for me. So you're saying because of the e to the I phi that you choose there,
yes.
Also in there is not an equivalent to the Hatano-Nelson if you would have. Okay.
Yes, the amplitude is the same.
Could you elaborate on the relation between higher dimensional translation and lower dimensional rotation?
Yes.
Is it always true for general quasicrystals?
No. So it's very special case. If we have, so how this happens is we figured it out for particular, this translation vector, where they have some, along these edges of window, if they have this extra sites, which maps to this physical space, only that happens, when that happens, then we have this additional, this quasicrystal structure subdimension. So it's not applicable for any translation. So if we do some arbitrary random translations, then it's nothing but we see some different region of this patch of this Anand-Binker type.
Thank you.
Are there other questions? I had a question so when you're thinking about the RKKY interaction between the spins, you'd also have an impact on like the conduction electrons. Have you thought about like how their conductivity would be impacted by scattering off of these spins?
Yeah, that's also another good question that I don't have answer for now. Yes. All right.
Okay, if there are no more questions, let's thank the speaker again.
Thank you.